So now that we've seen the stopped Martingale theorem, let's have a look at Doob's key theorems about discrete time process and how they extend to continuous time process, so the maximal inequalities and the convergence theorem. Now the good news is that this is going to be substantially simpler than what we've just done for the stopped Martingale theorem. Now the approximation process is just going to work in a much simpler manner. Let's have a look at it now. So the statement is almost exactly the same as its discrete time counterpart. It works for all sub-martingales that are non-negative, and what you get is a weak type 1-1 inequality. So the probability that the supremum of the process is large gets very low if you send alpha to infinity, as long as your process is in L1 and you're looking at a finite time interval, or in an infinite interval as long as your process is uniformly in L1. And then the supremum of your process, which a priori could be something much bigger, stays in L2 as long as your process itself is in L2, and at most you multiply the L2 norm by a factor of 2, and you have a similar control of all the moments of your supremum, of your maximal function associated with your martingale. Now the way we get this continuous time statement from their discrete time analog is by discretization, just like we've done before. So it's simple enough that I'm just going to do the proof here. We take our interval 0 to capital T, we discretize it into finitely many points that are at a distance 2 to the minus n of each other, and we give ourselves some n in n, and we're going to send that n to infinity. Now again, the continuity of the sub-martingale is going to be critical. So what the continuity gives us is what we have here, is the fact that the supremum of the process is really the limit of the suprema of the discretized processes, right? Now remember that up to a set of measure 0, my process has continuous paths, so there exists an A in sigma, it has probability 1, and for all omega in A, this t goes to m of t of omega is continuous. And then if you have a continuous function on a finite closed interval of the real line, its supremum is actually a maximum. So what we have is that for every omega in A, the supremum of mt of omega is mt of omega for some t. So there exists a t of omega in 0t, such that the supremum is a certain value. And now this value, if you take a n large enough, you're going to have that for, there always exists an n, of course. So there always exists a j in 0 till 2 to the n, such that tj minus t of omega is smaller than 2 to the minus n. So taking n large enough, you can approximate mt omega of omega by some mtj. So you can get this supremum of mtj, which a priori is smaller than the supremum of everything within any epsilon of the actual full supremum. And that's why you have this equality in the box here. Okay, so the supremum of your process is a almost sure limit, right, of these, right, I've written limit here and it's not clear in which sense, so this is almost sure of discrete processes. Now for the discrete processes, I have the Doob's inequality, right? You have the weak type 1-1 inequality, which is written here, and you have the LP moments inequality, or in particular the L2 control. Now all we have to do is use Fatou lemma to get the limit. We're going to have that, so we really, this is an expectation of some function raised to the power p. This is also an expectation. This is the expectation of the indicator function of that set. And so the limit of those expectation, or the limit of this, the expectation of the limit of these objects, which is what we're interested in, is going to be controlled by the lim_inf of these expectation, and this is controlled uniformly in n. And so you can take the limit and you get your result. So this is fairly simple because continuity gives us the almost sure convergence of the processes, and then Fatou lemma is enough because what we're looking at are really inequalities involving expectation to pass to the limit. Okay, so I'm going to leave that here and we're going to move to the Martingale convergence theorem, which will prove separately. It's a little harder, but not much harder. So what does the Martingale convergence theorem tell us? Same thing as before. Start with a continuous martingale. Again, let me emphasize that continuity is critical in all of these things we're doing. Start with a continuous martingale, assume it's uniformly in L2, then it would have a limit, and the convergence will happen both almost surely and in L2 null. So let's see the proof of this theorem. Now, one thing for sure is that if I have a martingale indexed by all the real numbers, I can look at the martingale, just at the natural number as point. So if I look at Mn, right, that's is a martingale with respect to Fn, because that's even true for all the real numbers t. And I have that the expectation of Mn squared, well, the supremum, if I take the supremum of all the natural numbers, this has to be smaller than the supremum of all the real numbers. And so by the theorem in discrete time, there has to exist a limit, right, such that Mn, now for n, a natural number that goes to infinity, goes to M infinity almost surely and in L2 null. Alright, that's exactly what the Discrete-Time Theorem tells us. So what we need is to show that the limit of the mt for t real is the same as the limit of the mn for n, a natural number. So let's have a look at that. We need to show that the limit, well, that limit may not exist, but let's say the limit sup of mt minus m infinity is 0 as t goes to infinity. Now, what can I say about this lim sup? I want to compare that to what I know about the natural number. So this is certainly the same as the limit when, let's say, m goes to infinity of the supremum over all t greater than m of mt minus m infinity. Right? It's just because it's a lim sup. And here I'm going to take m, a natural number. And now I can introduce m little m and say this lim sup is smaller than the limit. As m goes to infinity, I have to be a bit precise here, m being a natural number, supremum t greater than small m of mt minus mm plus the limit as m goes to infinity, m a natural number of m little m minus m infinity. That's by triangle inequality. But what I have here goes to 0 by the definition of m infinity as the almost sure limit of the mn for n natural number. So this lim sup that I want to show is 0 is smaller than this limit here, right? So what I first can do is I can replace m infinity, if you want, by m little m for m large enough because of the definition of m infinity. But now I could also do, I could take this sup and increase it by looking at t only in a finite interval. So I could take the supremum for t between little m and little n of mt minus mm, and this would be the same thing because as I said little n to infinity, I just increase that sup to that limit. Okay, so this is a good discretization that will allow me to apply the inequalities for discrete time processes, right? So the idea is that I want to look at the probability. So let's give myself some alpha. I want to look at the probability that lim sup of mt minus m infinity is greater than some alpha. And what do I want to show? I want to show that this probability is 0 for every alpha. And then, you know, you'll get that the this lim sup has to be 0 almost surely by just taking alpha of the form 1 upon capital N and an integer and just using the fact that a countable union of sets of probability 0 will have probability 0. Now, because this lim sup is smaller, as we've just seen, than this limit of supremum, I could use, say, Terminated Convergence to say that what I have here has to be smaller than the limit as m goes to infinity of the limit as n goes to infinity, and both of them will be natural numbers of the probability that the supremum for t between m and n of mt minus mm is greater than alpha. Okay, so what have I done here? So that's by Terminated Convergence, right? Because the probability of some set is really the expectation of the indicator function of that set. And indicator functions are smaller than 1, so they're always dominated. So, okay, so I need to show, I'm going to take some limits over natural numbers, but really what I need to do is control a probability of some supremum being greater than alpha. And I have Doob's inequality that do exactly that for me. So by Doob inequality, the weak type 1 version, I get that the probability that the lim sup of mt minus m infinity is greater than alpha, as t goes to infinity, has to be smaller than the limit m goes to infinity and the limit n goes to infinity. These are limits over natural numbers of, what do I get from here? I get 1 upon alpha times the expectation of mn minus mm, right? Because n is the endpoint of my time interval here. Notice that I've applied Doob's inequality with the sub-Martingale mt minus mm absolute value, and that's a sub-Martingale indexed by t starting at m, right? And that is indeed a sub-Martingale as an absolute value of a Martingale. Okay, so I get that for every alpha. Now, an N1 norm on a probability space is always controlled by the L2 norm, so this is smaller than the limit m goes to infinity. You can put the 1 upon alpha here. Limit n goes to infinity. Again, these are over natural numbers of the L2 norm of mn minus mn. But we do have convergence in L2 of the sequence mn by the Martingale convergence theorem in discrete time. So this is 1 upon alpha, limit as m goes to infinity, m in n of m infinity minus mm, and that limit is 0. Okay, so we've got that mt as t goes to infinity goes to m infinity almost surely. Very good. So we still need to show that this convergence also hold in L2. Notice, by the way, that like we've applied the Discrete-Time Theorem, but we wouldn't have been able to conclude the proof if we didn't have the Doob's inequality. That's what we've used here for a continuous time sub-Martingale, right? So we've used the full extension of Doob's inequality in order to get to that proof. Okay, so we have almost sure convergence. We need to upgrade that to get an L2 convergence also. And the way you do this, well, okay, let's have a look at mt minus m infinity in L2 norm for some t. And then let's say, so let t be a non-negative number. And let's take an n, a natural number that is above t. Right. Now, this is certainly smaller than the supremum over all s that are below t but above, let's say, the smallest integer below t of m s minus m infinity. Right. And this is kind of silly what I'm doing here, because of course t is in that interval. And it's above the smallest integer below it, and it's below n by definition of n. But the point is that I now have a supremum between two integer values. I'm going to use triangle inequality, and I'm going to decompose that into the supremum of, what is it going to be? It's going to be ms minus m integer, largest integer below t in L2 norm plus m of that floor t minus m infinity. Now the point is that, okay, as I send n to infinity, this is going to go to 0 because m infinity is the L2 limit of mn when n is a integer. And okay, and what I have here in the first term, I can use Doob's inequality for that, again the full force of them in continuous time, to control this by mn minus m floor t in L2 norm. Okay, oh, times a 2. So this is what we've got. And then we can send n to infinity, right? N was just some natural number above t. I can send it to infinity now, and I'm going to get 3 times m infinity minus m floor t in L2 norm. Okay, but now m floor t is a integer. So as I send t to infinity, the limit as t goes to infinity of mt minus m infinity is going to be smaller than 3 times the limit as floor t goes to infinity of m infinity minus m floor t, and floor t is a natural number, and so this limit is 0. That's well, by definition of m infinity, which came from the Discrete-Time Theorem. And that concludes the proof of the continuous time theorem.